All right. Our first unit, Unit 1, is on the physical Earth, and it deals with three spheres: the hydrosphere, atmosphere, and lithosphere. Those are the non-living parts of the Earth, what we also call abiotic. And basically, those particular factors on the Earth itself, and within different parts of the Earth are what determine what kind of living organisms will be there. So they revolve around temperature and water primarily, but there's also the air and the crust of the Earth and those kind of things. Those are other spheres that we talk about. But the primary one, the main thing that makes the Earth inhabitable by species is the presence of a large amount of liquid water, and we call that the hydrosphere. So one of the things about water is it has certain very unique physical properties, and this is helpful in two ways. One of the things is that these properties make it ideal for life, for cellular function, and then the second thing is that it makes the Earth physically habitable because water is such an excellent carrier of heat, and of course it's a liquid, so that the energy from the sun gets displaced and dispersed around the Earth. It doesn't make it super hot on one side and super cold on another, or super hot at the poles, at the equator, and cold at the poles, and that kind of thing. And so those things together have made it a very good place to live, if you will, in our particular solar system. So the majority of the water, of course, on Earth is in the oceans, and it distributes that energy from the sun and moves it around through ocean currents. And currents are driven by the wind on the surface, as well as the fact that they get denser. The water gets denser and sinks, and that drives what we call density currents. Be familiar, of course, with your water cycle. That's something you should know for a long period of time: condensation, precipitation, evaporation, etc. Got those kind of in the wrong order there, but one of the things that is usually new to students in AP Environmental Science is the aquifer, the dynamics of the aquifer. So this is something you need to make sure you're familiar with. The fact that water, when it falls as precipitation, can do three things, and this will become even more important when we look at water resources, in that it can sink into the ground and become part of the aquifer, or it can evaporate, or it can run off and form lakes and ponds and things like that. These are three of the sinks in the hydrologic cycle. So once it sinks underground, it can either be a shallow aquifer and just be the water that is directly absorbed in the ground and kind of sits down there like a sponge, or it may flow, and it does all flow, by the way. It's downhill, even underground towards the ocean. And sometimes if you have layers of what we call impermeable layers, like clay, where the water doesn't get through, you get a layer of a shallow aquifer and a deep aquifer. And a lot of times that deep aquifer, like we have a lot of here in Florida, comes from hundreds of miles away and is hundreds, if not thousands of years old by the time it comes out of the ground or is pumped out of the ground. So be familiar with your aquifer, your shallow versus your deep aquifer, and the properties of each. Okay. Then we have, like I said, our good old-fashioned water cycle. Make sure, in particular, you're aware of the transpiration factor of this. This is the biological part of the water cycle. This is important not only for trees. Trees use this process to, of course, pull the water up, but also to get the minerals out of the soil, to pull it up into their leaves and everything else, and then they forcibly vaporize the water from their leaves, so it increases humidity level more so than if there were no plants there at all. And what this does, it creates its own what we call a microclimate. So in particular in the rainforest, there's the atmospheric conditions that make the rainforest very rainy, but just the fact that because that and the excess sunlight of the equator, they get so many trees, the trees also create their own climate of even greater humidity and more rainfall in the rainforest because of that. Yes, Mr. Kelly.
Is sublimation like an important process at all?
Well, it's a minor problem. You should know it and understand it. It's a term that's you might see. So understanding and what we usually associate this with is dry ice because that definitely sublimes. Water also sublimes to a certain amount. It just means that usually it's the wind is blowing these water molecules off the top. It doesn't really go into a water state. But as far as a whole overall impact for the hydrologic cycle, yeah, it's not much. But just know that, just like advection basically is where the water in the clouds, remember this is liquid water, it's not water vapor, but it vaporizes from the sun typically, and then it'll kind of move and maybe go to a colder area and condense again into another cloud. So that's very common for evaporation and condensation to actually take place in the atmosphere and not have to go through the precipitation part of the process. So that's what advection is, and that's why that's important. Another term to be familiar with, make sure you understand infiltration. Think of filter, filtrate down. That's the process. That's just a fancy term for water soaking down into the ground. All right, then you have your ocean currents. So like I said, there's surface currents. These are driven by the wind. We'll explain how the wind currents go in a minute. But that's driven along. And then also, oftentimes the water will get colder or saltier and sink down. Of course, that's going to happen primarily in your polar regions. But you can also have from evaporation, you can have a certain amount of saltiness occur, sinks down, and then travels along the ocean floor and comes back up. This all, of course, from a physical standpoint, is important because it distributes heat throughout the Earth. It has a major impact on a lot of the climates that you see in these different areas, the land areas where these ocean currents go by. But also it distributes nutrients. This is important for life because when that water that's floating along, that's going along the bottom there, comes up to the surface, usually when it's pushed up against a continent or something, then it brings a lot of the nutrients, all that crap, literally, fish, organic waste and everything that's on the bottom comes up. Also, it's cold water, so cold water holds more oxygen, we know, and therefore you get a lot of productivity and everything in that area, the ecosystems where you have these what are called zones of coastal upwelling. So that's an important factor, is how ocean currents are important for life. That's just a detail of some of the water properties, etc. We didn't actually, let's look at El Nino real quick, because that's an important specific in the Pacific, if you will. And but it's often asked about on the exam. Come on, give me mine. Thank you. So you've got South America over here. You got Australia, and down here, great artist. And then you got the Pacific Ocean, of course. And what you have is that with the equator right about here, okay, is the normal flow thing just from the rotation of the Earth and something called the Coriolis effect. You have normal warm water currents right here at the equator that move along this way, and they go around like this, and then once they get past Australia, they hit the Antarctic current down here, and that kind of cools it off and pulls it down a little bit, and they sink and they go down along the bottom and kind of merge with the current that goes all the way around the Antarctic. But then they come back around, they're following this general counterclockwise pattern, that's what you're going to see in all your ocean currents that are in the southern hemisphere, and then the opposite clockwise pattern in the northern hemisphere, like our Gulf Stream. It goes along here. And then it gets pushed up here, and in this area, like I said just a minute ago, you have a lot of productivity. You've got nutrient-rich water, you got lots of oxygen in there, etc., because it's cold, and therefore you end up having a lot of fish, and that's just representing plankton, and of course from there you get your fish and everything else that eat. So very productive areas. So that's the normal situation. Now when you have an El Nino, the wind pattern really, it's called the El Nino Southern Oscillation. The Southern Oscillation part is the wind factor. This is called the trade winds here that pushes it along. This slows down. And so consequently, this gets backed up this way. And not only does that reduce the overall flow, coming up this way, the nutrients and everything, it means you also have warmer water here. So that drops the oxygen level, so it either kills or drives off a lot of fish. The fishing industry really suffers in that area. And then it results in, on land, it results in a very extended rainy season in this area. And that's actually where it got its name. The rainy season would extend into December, into Christmas, El Nino, the boy, the child, the Christ child. But all that is a... So you get that. You also, over here, when that happens, you get the opposite. So you get a drought in Australia. They also feel it in the Philippine area and stuff like that. Indonesia, drought, okay, excess of raining and stuff on this side, and it actually to the point where the sea level actually rises over here. It goes up, the sea level over here actually goes down. So over here, it's hotter, rainier, less fish. Over here it's drier and colder now. It doesn't really end up increasing the fish because you're not getting coastal upwelling there, but it's drier and colder in the West Pacific at this point. So this is east, this is west. Make sure you keep those. A lot of times they'll say like, what is the El Nino conditions would produce what in the Eastern Pacific or the southern or the western, southwestern Pacific, some area over there, and they'll want to know what kind of conditions will change for that. So make sure you're familiar with the El Nino, how that works and everything. You have to answer that as a question, describe it. Any questions about El Nino? Okay, ocean current, example of ocean current's effect. Alrighty, so review, look over the properties of water, that's the details, etc. in that, and that shows you water's distribution around the world. That's just kind of trivia, but you might want to look at it. See where everything is. Then we went all up into the atmosphere. And we talked about the composition of the atmosphere. In fact, one of the things about the atmosphere also, just like the water helps to distribute energy around the Earth, the atmosphere, this atmosphere helps to protect the Earth from high energy radiation from the sun. So it's another thing that makes things nice for living here on Earth. It's 79% nitrogen, 20% oxygen, or 78 and 21. I don't know, it varies. But you get numbers here, 70, 80, 20, 80-ish, with 1% left over of mainly argon. And the oxygen, by the way, comes from photosynthesis. That's an important factor here that you have to understand. Without photosynthesis, we would not have oxygen. Oxygen is a reactive element, and it took the process of photosynthesis evolving in life forms to put all the oxygen we have in the air right now, and that's a pretty high amount, you know, considering how little you have of everything else. So that is where that comes from. And then also remember that the atmosphere is in layers: troposphere, stratosphere, mesosphere, thermosphere. Colder going up, then warmer through the stratosphere, and then colder through the mesosphere and hotter through the thermosphere. The troposphere is pretty much where everything happens. Your weather, greenhouse effect, the greenhouse gases that produce the greenhouse effect, which we now know of. The only other thing that really has any other bearing or that's important for life on Earth is in the stratosphere is where you find the ozone layer. Okay, mesosphere, thermosphere, just know where they are, know that they're further out. There's not really much that happens in there, maybe the northern lights, but that really affects the Earth. Okay, and then we've got weather. So this is a combination, really, weather's a combination of the interactions of the atmosphere and the hydrosphere, evaporation, condensation. But what you end up having, there's your layers, is, well, we'll talk about actually wind patterns first of all. So we have certain wind patterns, as I mentioned just a minute ago with the ocean currents. They're either driven by the wind or they're driven by density differences. And so those wind patterns originate from the sun hitting the atmosphere at mostly the equator, so the air rises there and then it moves out and cools down and condenses and rotates like that, and it causes these cells to rotate in the opposite direction like gears, etc. And then the rotation of the Earth causes these twisted patterns of that, and then the fact that the air is going to cool and sink, etc. When that happens along that spinning surface, something called the Coriolis effect gives us these overall kind of circular patterns that we see across the globe, fairly even, regular patterns, whereas the wind is not that much affected by continents and things like that, like the ocean currents are. So you have more of a regular pattern of these circular things. So one of the things to remember there in particular is the fact that the air rising at the equator causes a lower pressure that causes more precipitation. That's why we have rainforests at the equator. That's all detailed out there. Then the opposite's happening. It goes 0, 30, 60, 90. It's evenly divided into thirds. So then the opposite happens when you go up 30. The air is sinking, and that sinking air causes high pressure. High pressure means less evaporation. Therefore, you find the deserts of the world along the 30-degree parallel. Go up another 30, opposite's happening, low pressure, 60-degree parallel. Tend to have a lot of snow in these areas. That's where you find the taiga forest. And then finally, at the poles, high pressure, theoretically, well, it's not theoretically, it's a fact. A lot of people don't think of it this way. But actually, that high pressure, Antarctica is the biggest desert in the world because of that. It has the least precipitation. You'd think it's very cold. You think there's a lot of snow. There's not a lot of snow there. Not a lot of snow in the tundra near the Arctic Circle. A lot of snow in northern Canada, in the taiga area where the air is going up and causing that precipitation. So be aware of those relationships. Here we see those wind patterns around. And now also, of course, they change yearly because of the, we're going to skip that for now, the process of the change in the season. So make sure you understand that. This is the fact that the Earth is tilted. And so this time of year, there's more sunlight on that lower hemisphere there. That's going to be winter for us, and summer for the southern hemisphere. There we go, like that. And then we keep running around, that tilt stays the same. Notice the tilt's the same all the way around. So here it's even. That's spring and fall. And then when it's summer for us, that's when that tilt is facing more towards the sun. And then we get the majority of the sunlight. Then our days are longer, etc. It's hotter, of course. Okay, so the importance for weather is that, of course, obviously you get winter and fall and all that kind of stuff. But also it will, in the tropic areas around here that don't really get the temperature change, it also pushes these air masses back and forth. And that's how we get our storm patterns and stuff like the that change in focus of the sun, what brings our hurricanes in. Well, we have a hurricane season in late summer, early fall, or actually in the mid-fall, almost late fall, as these air masses are moving down and interacting with other air masses. Questions about that? Know your different things like the Arctic Circle and roughly, I would know at least the month of when the different solstices occur. March, December. Well, that's March is an equinox, but the different things. December and June, and March and October, September. I guess I should know too, shouldn't I? All right. So then we go to the lithosphere. And of course, be aware, first of all, just simply try to remember that most of the Earth's crust is silicon, oxygen, and aluminum. Silicon oxides, aluminum oxides. Oxygen, therefore, is the main component of that in the Earth's crust. Also, the dynamics of the process of plate tectonics, the fact that the crust of the Earth is broken up in these big plates that are constantly moving around and interacting with each other, giving us things like earthquakes and volcanoes and those type of things. But be familiar with where and how they interact with each other, how the Atlantic Ocean is splitting apart and the Pacific's getting bigger, it's getting smaller as the Americas start to converge or moving towards across the Pacific Ocean into the Asian and Australian continental plates. So know your process, subduction and whether it's converging or diverging. We got those total faults, and then also transform faults. So know all those different interactions and know roughly where they exist, where they occur on Earth. And then also, the interior of the Earth, the fact that we have a liquid core, we have a solid core, but a liquid outer core, and of iron and nickel, and the fact that they're spinning like that creates a magnetic field. That's how we have, you have a compass works. You have magnetic north and south, and that whole fact shields us from a lot of the energy from the sun. So it causes it basically to go around us, and therefore you get the effects of the protection from that. All right, I'm getting off track here. Yeah. And finally, make sure you understand with the rock cycle process how that works together. There's your thing of that, and there's your different types of interactions. That shows you where they happen here. So make sure you understand this from this aspect of what this does for us. So it all sounds exciting and stuff, it's volcanoes and earthquakes, all those kind of things. But why is this even important really to life on Earth? The big picture here is actually the fact that what happens is the crust of the Earth is constantly renewing. It's getting pushed down back in the asthenosphere, mixing up, coming out in other places, forming mountain ranges. And then eventually, very long process of course, but this is how things happen, the water cycle then erodes these mountains, and as that water goes down slowly and surely and making its way towards the ocean, it spreads minerals and nutrients that plants and everything have to have. So that's why your river valleys and the areas around rivers that spread out are so rich and full of life and everything. It's also been why people have been able to exploit that. And the Nile River and Mesopotamia, etc., even the Indus River Valley, all is where civilizations have popped up because of this very fertile soil that exists there. So that's an important natural process. It's also, as we learn later, a process that's interrupted by dams by interrupting this sedimentation process. So be familiar with how that works and how it helps ecosystems. Questions, anybody? All right, we're going to stop Unit 1 here.